Hi, good afternoon. I'm Julian Leslie, Head of Networks and Chief Engineer for the Electricity System Operator. It's great to be here at COP26, actually in the Green Zone this afternoon, as this is where the public can come in and see the great innovation that's happening across many sectors, with next to Sainsbury's talking about food and Microsoft talking about their activities. It's also especially great to be here today on Engineering Day in the UK and really focusing on the engineering aspects of how we decarbonise a power grid. And I'm really pleased to be here with Chris from Reactive Technologies, who will introduce himself in a minute. But we're going to spend the next half an hour or so really talking about inertia and how we manage a low carbon grid and the activities we're having to take to sort of change and adapt and be ready for this transition into the future. It was really powerful yesterday that within the Blue Zone at COP26, where the diplomats are, that they launched the Glasgow breakthroughs, of which power is one of those breakthrough activities that we need to be really focusing on in order to get to net zero. And obviously this comes off the back of Boris Johnson at the Conservative Party conference a couple of weeks ago, committing the UK to have a zero fossil fuel electricity system by 2035. So it's really apt and timely that we're here today, and we're here with Chris to talk about this really innovative technology that's going to enable us to operate the system at low carbon grid. But before we get into that detail, Chris, can you just introduce yourself?
Great, thank you Julian, and so I'm Chris Kimmett, Director of Power Grids at Reactive Technologies. And Reactive Technologies has become a real expert in the grid stability space and in very, very high renewable, low inertia grids, like the UK. And we've always said that power grids are really the eye of the needle. You don't get decarbonised transport, you don't get decarbonised heat until you decarbonise the power grid. Electrifying everything means you need the clean power, and it's great to have these really ambitious goals for the power grid, and we'll talk today about some really innovative solutions about how we're supporting the stability of the UK power system.
Great, thanks Chris. I guess before we get into that, though, we should just reflect about where we've come in the UK and how much we have transitioned through this zero carbon journey already. You can see on the slides here that back in the 1990s, which was when I started at National Grid and the system operator, we were reliant upon 30-40% of coal pretty much every month of the year. Back in those 90s, you couldn't burn gas for electricity either, so you can see as we've come through sort of the early parts of 2000, the role that gas is beginning to play. But then very rapidly, as we get towards the 2010s and into the 20-teens, you can start to see the renewables start to pick up a fair share, and really the black sector really disappearing as coal is diminishing in its usage over the time. And you can see how the carbon intensity of the electricity we consume is really falling over this period. And then really in the last 3 or 4 years, you can really see the massive growth in renewables and zero carbon energy as we sort of get closer to today. And every year now we're breaking new records on the amount of renewables, the carbon intensity of our electricity, the largest offshore wind farm. And obviously the record we've just broken in the UK is the largest subsea cable to Norway, so bringing in that low carbon, zero carbon energy from Norway. So you can really see, gas has a critical role to play, and that's the big challenge now, is to how do we get from sort of 40% gas generation, how do we get to 2035 when we have 0% gas generation?
Absolutely. What I find really amazing about this progress is that we see a relatively high degree of stability across the 1990s. We see a bit of a shift from coal to gas, but it's really over the last decade that we've seen this sort of huge transition here. And this is, before the huge statements that were made at Paris, and then the huge statements that are being made here at COP26 as well.
And obviously from a system operator point of view, switching coal to gas from a sort of inertia and all those technical requirements, that is pretty much you swapping one for the other. But the big change over the last 10 years was diminishing that rotating mass on the system, diminishing the use of conventional power plant, replacing it with the inverter-based renewable technologies we have in wind and solar. That is what is really challenging system operators across the world. And that's why working with partners like yourself, finding these innovative solutions has become really important. And even though in the 90s we had that big energy shift from coal to gas, in terms of our system operation, we didn't need the same sort of focus and innovation that we're now having as we go from gas to renewables.
Absolutely, and the thing that doesn't come across in these time of visualizations is also the shift from the big transmission units more towards distribution as well. a solar panel on someone's roof is very, very different to a big spinning gas turbine. It's right at the edge of the power system, and so you start to get visibility issues as well. It's going from 50 big things to a million small things, more.
Absolutely, and that then brings in the other challenge that we have as a system operator, being able to forecast much more accurately. So in the past, we knew the technology people had in their homes, as a nation of 60 million people, were pretty predictable actually in what we do every day. But you now overlay that with the embedded generation, a lot of which is solar on people's roofs. As you say, we don't necessarily know where it is, and obviously it's hugely affected by cloud. To be able to forecast and predict all that. But what that is doing at the same time, though, is getting to the topic of today, really, because that is displacing the transmission-connected rotating mass that you get from gas-fired power plants.
Absolutely.
And that is the challenge of the system operators around the world. It's the one that we're sort of facing here, probably first, alongside with AMO in Australia and California ISO in the US as well. But we've all got the same technical problem, we're just approaching it from slightly different ways. And obviously what we're going to talk about this afternoon is how we're managing this here in the UK.
Absolutely, and I think it is, if you head over to the next slide actually, I think this is really, really applicable for other power systems as well. From 2013, we can see we have a relatively high intensity carbon grid, through to 2020 during lockdown when we had a very, very low carbon intensity grid. And we've made a huge impact and progress against the 2030 target already. And what I find interesting is that if we kind of apply this to other countries, we've seen this massive transition over the last decade. And I think that other countries will see this transition even quicker, maybe, particularly with some of the big ambitious goals aiming for 2030, where we've already made a large amount of progress and others are going to be really experiencing this snowball effect.
And I guess what these charts don't show is we've had a couple of times now where the market has delivered in the UK a zero carbon solution. But because of the activities we need to make to ensure we have a safe and secure and stable grid, we've had to interfere with the market really to buy on the conventional power plant to provide us the inertia, the frequency response and voltage control. And that's what the ESO's pathfinders and our ambition to be able to operate a zero carbon grid by 2025. That is what it's trying to do, is trying to look at that sort of 12% of actions that we took on that particular day to ensure that when the market does deliver us that zero carbon solution, that we're not interfering in the market.
Absolutely. So I guess we're here to talk about inertia. We've had a preview of the next slide already. So we should talk about what is inertia anyway. And I don't know if you want to give your engineering view. It's World Engineering Day, of course. And then I'll give my sort of layman's view, coming at this from an economics point of view.
I mean, inertia is a key component of operating a power grid, and it's for something that since the dawn of power grids, we've always had rotating machines creating the power. We've had rotating machines, motors sort of taking the power off the system as well. So all that stuff that rotates just gives it a real solid sort of stability, if you like, and it can withstand shocks. As we move to renewable generation, though, we don't have the same rotating things synchronously sort of connected to the network, because there's a black box between the blades on the wind turbine and the power that we receive onto the electricity network. Therefore, something we sort of got for free, physics gave us inertia on a gas-fired power plant or a coal-fired power plant. We're now having to think very differently because the physics of the generation isn't providing us the product that we need. So it's a real challenge for us and other system operators around the world, is how do you replace that? What is the alternative source of that inertia? Because it's so important. I know you have an analogy, Chris, but I also have two analogies. One is it's like a child's spinning top. And when you spin the spinning top and it starts making the sound as it gets up to speed, when you take your hand off, that thing keeps spinning for a period of time. That's inertia. And the other way we think about it is it's the ability to withstand shocks. So on a car going over a bump in the road, on a strong inertia system, as a passenger you don't feel it, but in a very light inertia system, the car will be jolted around quite significantly. So you don't have that damping force to sort of keep it under control.
Yeah, the analogy I always like to use is the grid of old, the one that was fueled by coal, is a bit like a steam train. It's very, very big. It's very, very heavy. It has these big spinning components in it, and so when it comes to driving that steam train, you have your regulator handle. You have the go faster, go slower. It's important to balance and get the speed right, but also it rides through faults. it's very, very sort of slow to react in a way. If there's a problem, it is really just going to sort of plaster its way through it. Whereas a modern power system with these lighter power electronics, they don't have these big, heavy spinning machines attached to them. That's more like trying to ride a motorbike. So the job in the control room is a little bit more delicate. One, you have to react a lot more quickly if something starts to go wrong. And two, you have to be able to do this a lot more in real time as well. So it really is a very, very different job. And inertia is fundamentally these spinning things. And these are spinning things that are on the transmission grid, so the big coal, gas, nuclear, hydro turbines, but also everything on the distribution network that's spinning. So if you look at big industry, you have fans, pumps, motors. Every water utility has water pumps that are pumping water up and down the country. And if we take a look, even in people's homes, we might have small motors in a washing machine or a fridge compressor that also might be a synchronous motor. So you sort of have the big transmission connected inertia. Then you've got the long tail of little bits of inertia as well that are actually very difficult to kind of understand and get your head around as well. You've got these, you can almost imagine these tiny little motors all connected up to this big machine, as well as these huge ones.
Absolutely, and I think to date, in the last sort of 3 or 4 years, we've had to try and model this. And the way we try to model it is that there'll be a frequency incident on the network, we bring out our models, we replay the condition that was actually seen in real time, run it through the models, and then tweak and enhance and really get our models to be really fine-tuned so that for that particular incident, at that particular time, we could understand and get confidence that the models that we've been using are giving us a good feel for all of these tiny motors and the big generators and how it all brings together. But obviously the network is so dynamic that whether your washing machine is on now or it's on in 5 minutes time and industrial units coming on or off, whatever. So actually we take these snapshots of moments in time, but what we don't have a good picture of today is that full 24/7 differences in generation and wind and all these other things, how all that comes together.
And it's a substantial amount. We found it's about 30% that comes from the distribution grid in the UK. In our studies with other system operators, the lowest we've ever found is 10%. And that was on a very, very small island grid with no industry at all. So it's at least 10% and up to 30%. I think as we go forward and we see these big transmission units disconnected, it will get even higher than 30% on the distribution grid. I think it'd be really, really interesting to cover kind of why inertia matters to the control room and what are the decisions that you take in real time. Why is a high inertia day with a really heavy grid, why is that different to a low inertia day with a really light grid?
That's a really good question, and in order to operate a grid, we need to make sure that it's safe and secure and reliable. And one of the key things and one of the key risks that are on the system is where you get a generation failure. It happens on a gas-fired power plant, it can happen on an interconnector, it can happen on an offshore wind farm, and suddenly you lose a big loss of generation. And that's where inertia comes in. If you've got a very heavy system, as you said earlier with your steam train analogy, you can sort of throw quite a lot of that and it still keeps going. The same thing on a heavy inertia day, so lots of rotating gas-fired power plant, you can lose one of those and actually the shock to the system is quite minimal and it can sort of carry on going and we've got a bit more time to bring on more energy to replace that energy loss. On a lighter system, you suddenly lose a 1200 megawatt interconnector to France, whatever it might be. That's a big shock to the system. And what happens then is the change in frequency, the rate of change in frequency is much greater. Therefore, you need to respond much more quickly to replace that loss of energy that's on the system. And that's what we've been doing over the last couple of years, is really thinking about our frequency management products as well, because there's a real strong linkage between inertia, we're really talking about here today, and frequency management. Because the less inertia you have, the quicker your frequency products need to be. If you have a lot of inertia, then you've got time to bring your frequency products in. So back in the 1990s, primary response was your energy had to be available within 10 seconds. If you think today, our dynamic containment product we launched a year ago, that has to be fully available within a second. So it just shows you that difference between the 1990s with a predominantly coal and gas-fired network. We could wait 10 seconds, the energy gradually comes in because this thing is going like a steam train. Whereas today on those light days, the minute you lose something, that energy loss is going to be brought in really quickly to arrest the fall in frequency and get that system back into balance.
You've got this motorbike and all of a sudden you need a very, very quick acting throttle to get you out of trouble, but then also the right amount of control on that throttle. So I know there's also a lot of thought that goes into the design of these frequency response markets, making sure that you have quick, but not too quick response, making sure that you don't end up with adverse reactions or ringing or oscillations or any other effects. So it is getting a more and more complicated picture.
It is getting more and more complicated, and our frequency response products have been more complex. So they're now dynamic, so they're monitoring the system frequency with sort of dead bands. They do various things at various times, whatever. So and all of this needs to happen automatically. If you imagine it's going to deliver in a second, you can't have human intervention in there. It's got to be something that is really monitoring the system in real time. And the faster, I mean, could we get to half a second product if we run the system even lighter on inertia? But at some point, we always need inertia because we need that stability, that robustness, that sort of stable platform in which we can operate the grid system from. So the way we do that today to ensure, from the models I spoke about earlier, we're making these models, we're looking at the generation mix that the market has delivered to us, we're making an assessment of the amount of inertia that we need. And in order to increase inertia, the activities we do today is we have to constrain off the renewable wind generation in order to create the space on the network to then bring on the fossil fuel gas generation that provides that inertia and those other sort of grid service products. And as I said earlier, that's the thing that we're now working towards, to try and reduce that and to make sure that by 2025 that we're not having to buy gas via power plant to provide inertia or short circuit infeed. And our Pathfinder projects will make progress that will make us towards that. But in order to know where we are second by second, minute by minute, in order to know how much inertia we need to procure in the market, first of all we need to be able to measure in real time what it is that we're dealing with here. So Chris, do you want to talk about your solution to that?
Absolutely, I'd love to. And yeah, we have something that's, relatively new on the market and relatively unique as well. So I'll first of all talk a bit of the background of reactive technologies and kind of where the technology has come from. So one of the first projects that we actually did with National Grid was about being able to send a signal through the power system. So we put a big load right in the middle of the grid, we turned it on and off, and we could measure that signal in any domestic plug socket anywhere in the power system. And that's because we have got a lot of ex-communication engineers who work for Nokia. Our R&D headquarters is in Finland. And as power system engineers, we like to talk in megawatts and we like to talk in hertz. And if you talk to a communication engineer, they talk about milliwatts and they talk about megahertz. And fundamentally, it's the same physics, but it's a totally different order of magnitude. So they saw the power system and they thought, wow, what a great place to be able to send a signal. And they did this project and they sent the signals over the power system. And in discussion with National Grid, they were saying, hey, this inertia thing is such a headache for us. Oh, why? Why is that a headache for you? Well, on a really high inertia day, it's really hard to send a signal through the grid, whereas on a low inertia day, it's relatively easy to send a signal through a power grid because you don't have this like big, heavy resistance to the signal anymore. And so we kind of developed that solution into a measurement platform. So to really characterize how that signal is propagating through the grid and to be able to take really, really accurate measurements for it. And I'm not sure if the slide is working, we're able to queue up the next one, but really our solution comes from three separate components. So there's one that we call the modulator. So that is actively sending some power into the power system and effectively trying to send a signal out to the grid. For the UK system, we've built an ultra capacitor, and I'll give some more details of that. For other projects, we've used batteries. We'd like to be able to use interconnectors in the future as well to generate these signals that we can inject in the grid and see how the grid's performing. In order to then sort of receive the signal, we have measurement units that we call XMUs. They're a bit like PMUs, but they're installed at the low voltage level, the very low voltage level. So in the UK at 230 volts, in the States at 100 volts, so that we can get the full view of transmission all the way down to distribution. And those are sampling frequency up to 48,000 times a second. They are looking for this very, very small signal. We're only injecting 5 megawatts into the grid. We have these massive offshore wind turbines where one turbine can deliver up to 5 megawatts. So it's a very, very small signal that we're injecting, and we have very, very, very granular, high-resolution data that's coming from our measurement units. That's then being reported into a cloud platform that we call GridMetrics. And that is where all the clever algorithms sit. So they know what signal has been sent into the grid. It's all GPS time aligned. They have the very, very high granularity, high frequency data stream, and they're able to align the two and understand what was the signal doing, what did we receive, and what does that mean for inertia? How are we actually able to use that propagation of the signal to understand fundamentally the physics of the power system? And because we're sort of treating the power system like a black box and effectively tapping it with a little hammer, we're able to get the totality view. We're able to understand what's happening at transmission, and we're able to understand what happens at distribution as well. So a lot of complicated stuff and algorithms, and what National Grid will see at the end of it is a user interface and an API. So you get the inertia data that you need off the back of this sort of complicated measurement infrastructure. We kind of see it almost similar to weather measurement. You know, there are people who float weather balloons, take very, very high granular detail of what's happening with the weather. They process that in supercomputers, they provide a forecast. What you really care about is how windy is it today. You know, you don't care about sending signals in the grid, you care about how much inertia there is today, and that's the data that we'll be trying to provide to you. The asset's just gone live, and this will be used from next year.
Which is a great step forward, because my concern with the models we've used to date is either we're right on the cliff edge and the models are great and we're in a nice, safe and economic and secure position, but as we said already, this thing changes second by second, minute by minute, and are there times today where we're a bit over the cliff edge, or are there times where we're a long way from the cliff edge and actually can run the system that little bit harder? So I'm really excited to start to get to see this data coming out, compare it with our models we've used to date, and really understand the impacts of this on the network. And Chris, is this the first in the world, or are you doing this anywhere else?
We've done pilots with batteries elsewhere, but this is the first in the world where we've done a system that's designed to be there for a long time. It's a multi-year contract. We have built a 5 megawatt ultra capacitor, which we can see on the next slide, up in Teesside. So this is actually just down the road from the world's biggest offshore wind farm. It's injecting power into the grid, so we have a 40-foot shipping container which is stuffed full of ultra capacitor cells, which are basically a bit like a battery, but a battery stores energy in a sort of in a chemical, whereas this is a little bit more like, you know, when you rub a balloon on your hair and it generates static. It's like the static electricity outside that balloon. We really want to be sending a signal into the grid every couple of seconds, and if you do that with the battery, sometimes you can experience issues with degradation. An ultra capacitor is super resistant to degradation because it's just static charge on a plate, fundamentally. So we have a shipping container that is crammed full of these ultra capacitor cells, 5 megawatts of them in total, and that is flowing through into an inverter system, and that's flowing through into the national grid, which is a couple of hundred yards down the road, through an 11 kV transformer and up. So this allows us to have a dedicated asset which is regularly sending this pulse into the grid and allows us to take the data and allows us to get this very, very accurate data over the long term as well. And it's great that it's based up near these other kind of world record, world-breaking projects as well.
And presumably it's pretty low maintenance, isn't it? It's maintenance free almost, or is there still?
Yeah, you have to clean out the air filters, but otherwise there's no moving parts. It's very much like any other sort of solid-state battery or ultra capacitor that you would find.
And are the TSOs around the world, are they watching closely what we're doing here in the UK and trying to learn from
Very much so, you know, all the way through from Australia and New Zealand, through Southeast Asia, a lot of conversations in the Middle East and the States as well. The UK and National Grid in particular is real leaders, you know. I think in the UK we're in a very, very unique position that we have a very large economy on a relatively small island. And so we've put a lot of renewables on that island, and we're really at the sort of the pointy end. We're experiencing a lot of the problems and having to create a lot of solutions for it as well. So National Grid is taking the first step, but a lot of utilities are looking at this project and looking at the inertia declining on their networks and looking at this as best practice in the field.
Fantastic, and it's great that we're here on Engineering Day in the UK talking about this fantastic engineering breakthrough that is truly leading the world and is going to be a key enabler for grids around the world to get towards net zero.
Absolutely, and my background's always been in software and algorithms, and it's been great to go and build a physical piece of kit. I'm sure you're probably the other way around it.
Well, no, it's great to see actually the products that go and the concepts that we start with a piece of paper. Actually, you see a photo now, something really physical is on the ground, and and as you say, over the next few months as we get to learn and use the data properly, it's going to really make a difference. I guess it's the beginnings though. Now we're measuring inertia, we get to, so what do we do with that? So as you know, we've already got the Pathfinder processes running, so Pathfinder Phase 1, we signed contracts just 18 months ago. We've already had, I think it was a slide, we've already had Deeside, an old gas-fired power plant that's repurposed itself to provide solely inertia at 0 megawatts, which is Kraken, which is a well-established hydro plant that's now operating in a very different way, that's providing inertia, and Statkraft have worked with GE as well to develop this innovative grid-stabilizing solution, which is it's a rotating machine, but it's really, really heavy, so it provides a lot of inertia for quite a small package. And as we look forward into Phase 2, stability in Scotland, really looking at not only just inertia, but short circuit infeed as well, which is another key grid stability factor. And then we're going through Phase 3, which is looking really at England and Wales, and really looking at the inertia that we need across the entire system. And because what we're doing in the ESO, we're defining what our need is. So we're defining the technical requirement, not the solution.
Yeah.
So what we're getting through these Pathfinders is huge innovation. You can already see, we talked about three different approaches here. As we go into Phase 3, and then maybe as we go forward after that, we're getting to see virtual synchronous machines, so actually using the power electronics and probably using some capacitors actually to sort of work together very quickly in order to provide synthetic inertia. And once we can do that with solar and with wind and with batteries, whatever, then suddenly we're back to a network with many, many sources of inertia again, albeit synthetic.
Absolutely, and nobody should kind of take away from this the doom and gloom picture to say, oh, renewables are coming and it's all very, very difficult. There are solutions in the short term, which is all about those control room actions you were talking about. Maybe bringing some of the interconnectors down a bit or the renewables down a bit temporarily and then allowing them back on when you've got around the constraint. There's medium-term actions around buying more frequency response and faster response, and there's plenty of these long-term solutions as well, be it building new spinning masses or building very, very fast-acting synthetic inertia from inverters, from grid-forming inverters. But fundamentally, whether you're looking at the short, the medium, or the long term, the starting point has to be what is the baseline, what is the inertia that's out there already, both on transmission and distribution, so that you can get what is the right technical need, what is that gap that I'm trying to fill, and also so that you can kind of assess these solutions over time as well. Is that inverter really delivering the response that I thought it would? Are there any other adverse effects around it? How do I kind of make sure that it's still doing what it said on the tin? So we think there's a really, really critical role in very, very accurate data across all those timescales to inform the right investments that we need to make ahead of net zero.
No, absolutely, Chris. And there are those solutions out there, and the beauty about these solutions is they're carbon free and they're cheaper than the alternative. They're cheaper than running a gas-fired power plant. So as we bring forward these solutions on the network, the cost of running the network is going to start to fall from where it is today, which is a fantastic thing. It's not only enabling net zero, but it's also reducing costs to consumers.
Absolutely, and that's the whole message for COP26 and the whole message for this movement is we're not going into a doom and gloom future. We're going to one with abundant, clean, cheap energy and a far better future with electric vehicles, with electric heat that are powered by these renewables and powered by this clean generation.
Absolutely. And it's obviously down to the system operators to try and work out how this whole thing sort of comes together, and it's through great innovation, through organisations like your own that are going to come together and make a real big difference, and we can solve these engineering challenges that we're facing today. We can see that route to 2035 here in the UK for a zero carbon electricity system, and that'll set us on a good path then to the whole societal sort of net zero by 2050, so that's really exciting. So I think, Chris, well, thank you for that great conversation. Hopefully everybody watching has learned something about inertia and how we're now going to measure it and why it's so really, really important, not only here in the UK, but across the world in decarbonising grids. And it's great to do this from COP26 in the Green Zone. I mean, what a such an appropriate environment on Engineering Day as well to talk about a real big engineering challenge for grid system operators around the world.
Absolutely. It's been a pleasure. Thank you, Julian.
So thank you very much.